Hi everyone, we are going to take a look at Unit 1, which is our Atomic Structure and Properties unit, and we're going to look at topic number 1, which covers Avogadro's number and moles. So you had a little bit of review on this, and now we're going to go a little more in depth on new information. So Avogadro's number, Amadeo Avogadro did research in gases and first proposed that the volume of a gas, so how much space a gas takes up at a given pressure and temperature, because gases are really affected by those two things, is proportional to the number of atoms or molecules in that gas, regardless of what kind of gas it is. So what he's saying is that if we have a specific volume of gas, say you have a liter of gas and it's at a specific temperature and a specific pressure, then no matter what the gas is inside, it's always going to be the same number of atoms or molecules. So I could have helium there, or I could have carbon dioxide, or I could have methane gas. All of those, if I had a liter of it at the same temperature and same pressure, it would be the same number of particles. So it was this concept was later confirmed, and the number of particles that other scientists researched and came up with and calculated for this constant was 6.022 times 10 to the 23rd power. So that has been named Avogadro's number to give credit to the research that he did around this concept. So check out your equation sheet that was passed out for AP Chem. This is on there, so take a minute and find it. When you see it, it will appear a little bit differently. So it will appear, there's my pen, like this. And you might look at that and go, okay, well, what's those units? Why does it have a -1 after it? What's going on there? So what this is saying, when we have a negative unit like that, or a unit with a -1, it's telling us it's in the denominator of a fraction. So what this really means is that we have 6.022 times 10 to the 23rd particles, atoms, molecules, whatever the particle is, per mole. So when we have that division sign, we say per mole. So what do we really mean by that? It means that if we have a mole of a substance, in that chunk, there are 6.022 times 10 to the 23rd particles, right? So it's a counting unit. It's a way to take something, to count particles of a substance easier by grouping them. So one group we're calling a mole, and in that group there are 6.022 times 10 to the 23rd particles. So if we had 2 moles, that would be 2 groups. Each one would have that same amount, so we'd have a total of 12.044 times 10 to the 23rd particles. Okay, if we had 3 groups, 3 moles, we'd have 3 times that amount, right? So each group has the same number of particles. So instead of having to list out how many atoms or molecules there is in something, we can just say, hey, we have a mole. We have 1.2 moles. We have 6.3 moles, right? We have 12.2 moles. We can say groupings instead of how many total individual little teeny tiny particles there are. And it's a little bit easier because we are dealing with things that we can't see and are very small. So we need to put them in big groups so that we can actually have a substantial amount. So calculations with Avogadro's number. Now that we have the number, we can do some calculations with it. We can add it to our toolbox. So some things that you've already done in chemistry that you kind of have in your toolbox already is we know how to find molar mass and relate the molar mass to grams. So we can convert between the mass and the grams of a substance. We've learned before how to relate the moles of a substance to the volume of a substance, of a gas, right? 22.4 liters is 1 mole of gas at STP. We've also learned how to relate the chemicals to each other using a balanced reaction, which is our mole ratio. So we have the mole ratio and can relate those amounts of chemicals to each other. Now we're going to add Avogadro's number to our toolbox and use it to do some calculations. So the types of problems that require Avogadro's number are when a specific number of particles, atoms, ions, molecules, electrons, whatever particle you're talking about, are given and other information is asked for. So you can use Avogadro's number to convert the value that you're given to moles and then do other calculations that might be necessary for the problem. Alternatively, a problem may give you a value and ask you to find the number of particles. So it's asking how many atoms are there? How many electrons do you have in this substance? How many ions are there present in a solution? So you would get the given value, whatever you're given, we want to get it to moles first. So that's our first goal, is get it to moles. And then we can relate those moles to Avogadro and use Avogadro's number to get it to the number of particles. So Avogadro's number goes from number of particles, the individuals, to moles, that group, or we go from the group of moles down to how many particles we have, okay? So we're going from that teeny tiny microscopic level to these groupings. So let's take a look at an example. This one says how many moles of nitrogen gas, so we're looking for how many groups, are in a sample of 5.39 times 10 to the 24th molecules. Okay, so let's take a look at this. A mole, what it's asking for is a group of particles. So it's really asking how many groups can we make from the amount we're given. We know one group is that 6.022 times 10 to the 23rd, right? Avogadro's number is a mole. So take a second, pause for a minute, and think about how this math may need to be set up to work this out. Think about what would you have to do with this given amount. Should our answer be large? Should it be like something in scientific notation? Or should it be smaller? Do we need to divide or do we need to multiply by 6.022 times 10 to the 23rd, Avogadro's number? What's going to make this make sense if we're looking for how many groups there are? So pause and think about that. All right, so hopefully you've kind of thought about it and maybe come up with something. So let's check out if you're on the right track. So in calculating anything like this, we want to set up our railroad tracks. It's a conversion. And set up our units. So as always, we're going to copy our unit down to the bottom to get it to cancel. So molecules of nitrogen, just making it match. And we want to go from that individual molecule to how many groups it is, how many moles there are. So we got moles of nitrogen. It's all nitrogen. That chemical is not changing. So we can think about how this part here relates together, okay? So I always like to think about the mole first. So in one mole, how many molecules do we have? So well, in any mole, we have 6.022 times 10 to the 23rd, that Avogadro's number of particles. In this case, our particle, our chunk, is a molecule of nitrogen, those N2 chunks, right? So what we're doing here is we are going to multiply by 1, but we're really dividing by that Avogadro's number. So if you thought about this and you said, hey, I'm going to have to divide this by my Avogadro's number to make this make sense to get how many groups we can have, then you are on the right track. So when we do that, again, we put it in our calculator. We're using that special E button, right, to put that times 10 in, make sure it's entered correctly. This is a good way to check yourself and make sure you're putting it in correctly. We should get about 8.95. So try it in your calculator, make sure you got that. And we can check our significant figures as well. Remember, in scientific notation, we count anything in front of that times 10. So there's 3 digits in our given value. So we want 3 significant figures in our answer. All right. Our next one, how many moles of electrons are in a sample of 1.3 times 10 to the 22nd? So again, we're asking for moles. We're looking for how many groups there are when we have this many electrons. Now you notice I didn't put atoms or molecules because the particle we're talking about is an electron. So it's a little bit different. So we want to go from electrons, how many electrons we have, to how many moles of electrons we have, right? How many groups of those do we have? So think about where your Avogadro's number might need to go. Again, just like our last one, we have 1 mole of electrons. So 1 mole is equal to Avogadro's number. So we set up our fraction there. So again, we're going to be dividing, and we'll be left with moles of electrons. So we're looking for those groups, so we should have a smaller value, right? And this is not even a whole group. If we look at our given value, we have 1.3 times 10 to the 22nd. That's not even 1 mole. So we should get less than 1 for our answer. So we have 0.022 moles of electrons when we divide that. And again, looking at our significant figures, there are 2 in our given value, and our answer has 2 significant figures because leading zeros do not count as significant, but we do have to write them. All right, let's take a look at another one. How many atoms of helium are in a sample of 6.23 moles of helium? So we've got this time moles of helium. So we've got the groups. We've got 6.23 groups of helium. We want to know how many actual helium atoms do we have? So take a second again. Think about, are we going to have to multiply or divide by Avogadro's number? So let's set up our units. We're going to copy those units to the bottom, moles of helium. We're going to put our atoms of helium. That's what we're looking for, how many individual atoms there are on top. So in 1 mole, there are Avogadro's number worth of atoms, of particles. So this time we're going to have to multiply, right? We know we have these 6 groups. In each group, we have the Avogadro's number. So we're going to multiply that out. And we get 3.75 times 10 to the 24th. Again, we have 3 significant figures given. We've got 3 significant figures in our answer. All right, atoms of helium. Make sure you're writing down your times 10 to the 24th, that you're getting that part written. Sometimes I'll have students get done and they'll just write 3.75 because they didn't check their calculator, they didn't keep reading, and they didn't notice the times 10 to the 24th. So if you just write 3.75, that is incorrect and you will miss that question. Okay? So be careful there. All right, so let's look at combining calculations, how this might work. So we can combine this tool using Avogadro's number with others that we learned in honors chemistry that I mentioned before to answer more questions. So this is an example of another type of question. So it says, how many atoms are there in 20 grams of calcium? So we don't know how many groups we have. We don't know how many moles we have. We just have the mass of it. We know we have 20 grams of calcium. So it's on a balance. We've weighed it out. That's how much we have of calcium. So we want to get it to how many groups are there of moles. And then we're going to relate it to how many atoms there are. So first, we can change our grams of calcium into moles of calcium. And we do that using something we practice, molar mass. How many moles relate to our mass in grams? So we look up on the periodic table. Calcium's molar mass, since it's just calcium, it's not a compound, is 40.08 grams per mole. So we're going to put the 40.08 next to the grams. And when we say per mole, we talk about 1 mole. That cancels out our grams of calcium. And then we can keep going. We copy our unit, moles of calcium, to the bottom. And what we want is atoms of calcium. So again, this is going from how many groups do we have to how many individual atoms. Now we don't know yet how many groups we have because we haven't done this first part of the math, which is fine. We can do all of our math at the end, but we can still set up our ratio. So in 1 mole, we know there are Avogadro's number worth of particles. In this case, our particle is the atom. And that allows us to cancel our moles. And now we're left with just those units we want. So we can multiply 20 times Avogadro's number and then divide by 40.08. Try that out in your calculator, see what answer you get. Think about your significant figures and then check your answer here. So we should get 3.00 because we do want to count our significant figures. There are 3 in our given value. We're counting from the left side, everything after our first non-zero digit count. So there's 3 significant figures there and there in our answer. So 3.00 times 10 to the 23rd atoms of calcium. So let's notice a couple of things. Avogadro's number is about 6 times 10 to the 23rd. We have about half of that here for our answer. Well, why would we have about half of that? Well, let's look at our value. We've got 20 grams of calcium divided by about 40 grams of calcium, right? It's molar mass. We have about half a mole of calcium, right? We have half its molar mass. So if we have half a mole there, we're going to have half of Avogadro's number because that's half a mole, right? So we can kind of see that those are ways of estimating, thinking about the numbers, and checking your work. All right, last part. Let's take a look at another way to look at the amount of a substance. And it's using percentages. So we have something called percent composition. Percent composition tells you the amount of a particular chemical within a larger substance, either a compound or a mixture. So it could be like how much carbon is in carbon dioxide, that molecule. Or it could be how much sodium chloride is in a mixture of sodium chloride and water, like salt water, right? So it could be looking at a particular part in a mixture or a particular element in a compound. It can be used for both. Percentages are great because they are always set up the same way. They're found by dividing the part you're looking for by the whole thing. Whatever the whole thing is we're talking about, we're going to take the part we're talking about, divided by the whole thing we're talking about. And then we multiply by 100. And typically this is done using the mass of our substances. So it could be masses that are given in an experiment. Maybe you have a way of isolating one piece and you find the mass of it, and then you have the total mass of all your substances and you're finding the percent that way. Or we can use, if we have no information, like this question here, what is the percent composition of hydrogen in CH4? CH4 is always the same formula, so we can use our molar masses for this. So let's see how this might be set up. So again, we want to take the mass of the piece we're looking at. This is looking at for hydrogen. So our total mass of hydrogen would be 4 hydrogens from our chemical formula times their molar mass, 1.01. And then we want the mass of the whole thing. Well, the whole thing that we're looking at is CH4. So we've still got those 4 hydrogens, plus we've got a carbon atom, right? We got that carbon. So there's our mass of carbon. So our total in our denominator is about 16.05, and our numerator is about 4.04. We're going to multiply that by 100 to make it a percentage. So we divide these two values, multiply, and we should get about 25.2% hydrogen in CH4, right? So if we did the top part, we'd have about 4.04, and the bottom we'd said was 16.05. Forgive my terrible writing on this, 16.05. So we can see 4 out of 16, that's about a quarter, right? So 25.2 is a very reasonable answer. So about 25% of CH4 is hydrogen, and the other 75% is carbon because it has a bigger mass. So even though there's more hydrogens, carbon has a bigger mass, so it makes up more of the total mass of the chemical. So that's how percent composition might be used. Okay, so total mass of the, or mass of your piece over the mass of the whole. Part out of the whole, right? Last thing is relating this to labs. So how might this look gathering data? So there are a number of ways of determining the amount of an element in a particular chemical, or the amount of a compound, like a compound in a mixture. So typically mass measurements are made with large samples of a substance, samples we can manipulate in the lab, and either a reaction or some sort of separation is done to determine how much of a single element or a single compound is gained or lost during that reaction. This can allow us to do calculations to relate the amount that changed to the amount in our mixture or compound. So for example, you have a substance, it contains water, right? We can heat that up and get rid of the water, right? Boil away the water. And the difference between your mass before with everything and your mass after heating will determine the amount of water in your original sample. So we can use that information to find out how much water we have. We could take that mass of water and convert it to moles. We could convert it to molecules of water, all of that stuff. So using the tools that we've gained through this. So big thing here is to, if you're given like a lab situation, pay attention to any chemical reactions given. Look at states of matter. If something is a gas, that means it's leaving. So we're getting rid of that. That's going to be the piece that's reducing the mass. Look at the process described in the prompt to help you determine any changes occurring. So are they separating or filtering or heating, or what are they doing to separate things? And then use the data that's given to help you in your calculations, to help you figure out what's the differences, right? So this should help you in your practice. Remember, ask lots of questions in class if you need any help on this. And I will talk to you guys later.